There are many different energy resources. Which two energy resources are renewable? Renewable means that the resource will not run out. So we see immediately that coal and gas are both fossil fuels. These are made over thousands and thousands of years, so they are non-renewable. They're going to run out eventually. Biofuels are produced from plants, so they are renewable. Geothermal energy comes from energy released by radioactive substances deep within the Earth, and they get the energy from the heat in the Earth. Since this is a natural process, it's renewable. Nuclear fuel. So nuclear fuels are elements, and these will eventually run out, so they are non-renewable. Which means our two answers are biofuel and geothermal. Some non-renewable energy resources are more reliable than others. Which statement correctly describes a reliable resource? Something that is reliable is something that behaves in the way you expect. Another word for behaving in the way you expect is predictable, so this one is the answer. Not burning fuel is not what reliable means. Never run out is renewable. And cheap is also not what reliable means. Figure 1 shows a wind farm. You can see there's a wind farm with 7 wind turbines. The total power output of the wind farm is 19.6 megawatts. All of the wind turbines have the same power output. What is the power output of one wind turbine? So there are 7 turbines, and a total power output of 19.6 megawatts. And if all 7 turbines have the same power output, each turbine will have a power output of 2.8 megawatts, because it's 19.6 divided by 7. Figure 2 shows the electricity generated by different energy resources in the UK. The total amount of electricity generated was the same in 2014 and in 2015. The two pie charts show the different proportions of the different energy resources used in 2014 and 2015. There are changes in the amounts of different energy resources used between 2014 and 2015. Explain the environmental impacts of the changes. To answer this, first of all we need to spot the changes from the pie charts. We can see that other fuels was the same percentage in both 2014 and 2015. Renewables increased by 6%, because 25 minus 19 is 6. Gas also stayed the same at 30%. Nuclear increased by 2%, because 21 minus 19 is 2. And coal decreased by 8%, because 22 minus 30 is minus 8. Now that we've spotted these changes, we need to explain the environmental impacts of the changes. So we can start by talking about coal. We can see from the pie chart that the percentage generated by coal decreased by 8%. This means that less fossil fuels were burnt. But what are the environmental impacts of this change? So when coal is burnt, carbon dioxide is released. So if less coal is burnt, less carbon dioxide is released. Carbon dioxide is a greenhouse gas, and greenhouse gases contribute to global warming. So less coal being burnt means less greenhouse gases emitted, which means less global warming. So in this question we identified a change, which is the change in the percentage of coal, and then we explain the environmental impact of the change about global warming. So to get more marks we need to repeat this process again. So we need to find another change, and one of these is the percentage generated by nuclear power increased by 2%. But what effect does this have on the environment? Well, when you use nuclear power you get a dangerous byproduct. So when more nuclear power is used, more hazardous waste is produced. To get 4 marks, you need detailed points, which are logically linked. You also need as many indicative points as you can. You get an indicative point for percentage generated by coal decreased by 8%, another for less fossil fuels burnt, another for less CO2 released, and for less greenhouse gases emitted, and for less global warming. Percentage generated by nuclear increased by 2% is another indicative point. More nuclear fuel used is another one, and more hazardous waste is another one. Other indicative points you could have included in your answer would be less environmental pollution, less acid rain, and percentage of gas remain the same. Figure 3 shows a mobile phone being recharged by a portable power source. So here's the portable power source, or portable charger as you might know it. Why does the battery in the phone need recharging? Is it because the store of chemical energy in the battery is reduced? Is it because the store of thermal energy in the battery was reduced? Or is it the store of kinetic energy or the store of gravitational energy? Is the energy store in the phone a chemical energy store? Well, chemical energy stores include fuels, food, or chemicals found in batteries. So this could be our answer, but we'll check the others to make sure. Is the phone powered by a thermal energy store? Well, thermal energy stores describe the energy a substance has because of a temperature. So if the phone was powered by a store of thermal energy, if it had a battery of 100%, it would be really, really hot, and if it had a battery of 10%, it would be much, much colder. And we know that this isn't the case, so this isn't our answer. Is a phone powered by a kinetic energy store? Well, kinetic energy stores describe the energy an object has because it is moving. There is nothing moving in a battery, so this isn't the answer. Is the phone powered by a gravitational energy store? Gravitational potential energy stores are used to describe the energy stored in an object because of its position. If a phone was powered by this type of energy store, the battery would be moving position, moving up and down, moving height, and that's not the case, so that's not the answer. So the answer is the store of chemical energy in the battery is reduced. The power source provides a current of 1.86 amps at a potential difference of 3.9 volts. Calculate the power of the power source. And we're given the equation for power as power is potential difference times current. Choose the correct unit from the box. So we're asked to calculate power and we're given the equation. So we need to substitute the values in for potential difference and current. Our potential difference is 3.9 volts and our current is 1.86 amps. Before we do this, we need to check the units are correct. Volt is the correct unit for potential difference and amp is the correct unit for current. So we can put these into our calculator to get an answer of 6.254 for power. But what is the correct unit? The unit for power is the watt, which we use a W to represent. C represents a coulomb, and this is the unit for charge. J represents a joule, and this is the unit for energy. And W represents the watt, and this is the unit for power. We get 1 mark for this calculation here, 1 mark for our value for power, and 1 mark for the unit for power. A student needs a new power source. Figure 4 shows 3 different sized power sources: compact, large and high capacity. Table 1 gives data about the 3 different power sources. You can see the number of charges each power source has, which is the number of times you can charge a phone with the power source without having to recharge the power source, and also the mass in grams, which is how much it weighs. And they give you this information for each, the compact, large and high capacity power source. The student chose the large power source. Suggest why the student chose the large power source. What would a student want in a power source? Well, you'd want the number of charges to be high because you want to be able to use the portable charger for long periods of time and use it over and over again before having to recharge it. You'd also want the mass of the power source to be low because you wouldn't want something really heavy to have to carry around with you. The student probably wouldn't choose the compact power source because while it is only 100 grams and the lightest power source, you can only charge one phone before you have to recharge the power source, which isn't very useful. A student might also not want to use the high capacity power source because while you can use it 10 times before you have to recharge it, it weighs 600 grams, which is really quite heavy to have to carry around with you. Another way you could look at this is compare the large power source with both the compact and high capacity power source. The large power source has 5 times the number of charges as the compact power source, with only 2 times the mass. This means you would want to use the large power source over the compact because you get more charges for the mass. Now we compare the large power source with the high capacity power source. Although the large power source has half the number of charges as the high capacity power source, it only is a third of the mass. This is a reason to choose the large power source because you get more charges for the mass. You get 1 mark for this point, 1 mark for this point, 2 times the mass. Then you get another mark for saying the large power source has half the number of charges as the high capacity power source, and another for saying it's a third of the mass. Another way you could have chosen to phrase this is you could say that the student chooses the power source with the highest charge to mass ratio. The higher the charge to mass ratio, the better. The compact charge to mass ratio is 1 divided by 100. The large charge to mass ratio is 5 over 200, or 1 over 40, and the high capacity charge to mass ratio is 10 over 60, 600, which is equal to 1 over 60. You can see that this is the greatest number, 1 over 40. So the large power source has highest charge to mass ratio. And if you choose to answer the question like this, you get a mark for each of these. Figure 5 shows a girl skateboarding on a semicircular ramp. As a diagram, you can see the maximum height of the ramp is 4 meters. The girl has a mass of 50 kilograms. Calculate the gravitational potential energy of the girl at the top of the ramp. Use the equation gravitational potential energy is mass times gravitational field strength times height, and we're given the gravitational field strength of 9.8 newtons per kilogram. So if we're asked to calculate the gravitational potential energy, and we're given the equation here, so we need to find the mass, the gravitational field strength and the height. We're given the gravitational field strength in the question of 9.8. We're given the girl's mass of 50 kilograms. So what is the height? We're asked for the gravitational potential energy of the girl at the top of the ramp, and if we look at the diagram, the maximum height is 4 meters. So this means the value for height is going to be 4 meters. So the gravitational potential energy is 50 kilograms times 9.8 newtons per kilogram times 4 meters. Before we type it into our calculator, let's check the units. Kilogram is the standard unit for mass, newtons per kilogram is the standard unit for gravitational field strength, and meter is the standard unit for height. So we can type this into our calculator and get a value of 1960 joules, because joules is the standard unit for energy, so we don't need to do a conversion. So the answer is 1960. We get 1 mark for the calculation and 1 mark for our final answer. The girl has a speed of 7 meters per second at the bottom of the ramp. Calculate the kinetic energy of the girl at the bottom of the ramp. Use the equation kinetic energy is half mass times speed squared. We want to find the kinetic energy, and we're given the equation for kinetic energy here. We already have the mass, it's from the last part of the question, and it was 50 kilograms. And we're also given the speed in the question of 7 meters per second. So we need to plug these values that we're given in the question into the equation. So we have 0.5 times 50 kilograms times 7 meters per second squared. Before we put that into our equation, we need to check the units. Kilogram is the standard unit for mass, and meters per second is the standard unit for speed. So if we type that into our calculator, we get an answer of 1225. We worked out energy, so the unit is joule. We get 1 mark for the calculation and 1 mark for the final answer. Not all of the gravitational potential energy has been transferred to kinetic energy. Which two statements explain why? Is it because some energy is wasted? Maybe some of the gravitational potential energy was transferred to other things, such as work done to overcome friction or sound. But this could be a reason why not all the gravitational potential energy has been transferred to kinetic energy. Is it because the mass of the girl is too low? The mass is going to affect the gravitational potential energy, and it's also going to affect the amount of kinetic energy. But it's not going to affect the proportion or the amount of the gravitational potential energy that's transferred to kinetic energy. So that's not an answer. Is it because the ramp is not high enough? Again, the height does affect how much gravitational potential energy the girl does have at the top of the ramp, but it doesn't affect how much of the gravitational energy is transferred to kinetic energy. So that's not one of the answers. And again, that's the same with the speed. The speed affects how much kinetic energy there is, but it doesn't affect how much of the gravitational potential energy transfers to kinetic energy. Is it because the gravitational potential energy of the girl is not zero? If we think about the ramp, we know that at the top, the girl has some gravitational potential energy and no kinetic energy. If we assume that at the bottom of the ramp, the gravitational potential energy is zero, all of the gravitational potential energy here is transferred to kinetic energy, apart from the gravitational potential energy that's wasted through friction or sound. However, say for example, the gravitational potential energy at the bottom is equal to 50 joules, and the gravitational potential energy at the top is equal to 100 joules. Here, assuming none of it is wasted, the kinetic energy is going to be 50 joules, because there's also 50 joules of gravitational potential energy, because maybe the ground is down here. So the gravitational potential energy of the girl not being zero at the bottom of the ramp is a reason why not all the gravitational potential energy is transferred to kinetic energy. So these two must be our answers. Explain how lubricating the wheels of a skateboard can increase the speed of the girl. Use ideas about energy in your explanation. Lubricating is making something more slippery by reducing the friction. Friction is the force that opposes the direction of motion when two objects rub over each other. In a system without friction, all the gravitational potential energy would be transferred to kinetic energy. However, in a system with friction, work has to be done to overcome the force of friction. This means there is less energy left for kinetic energy. So you can see that the more friction there is, the more work has to be done to oppose the friction, so the less kinetic energy. Lubrication reduces the amount of friction. So more energy is transferred to friction rather than wasted, or more energy is usefully transferred. This means there is greater kinetic energy. And if there's a greater kinetic energy, there's a greater speed. You get 1 mark for reduces the amount of friction, 1 mark for more energy is usefully transferred, and 1 mark for greater kinetic energy. Some ceiling lights in the home are connected to the mains by a 2-core cable. Figure 6 shows a ceiling light. Suggest why some ceiling lights do not have an earth wire. So the earth wire is a safety precaution, and it is there to stop the appliance, or in this case the copper wire, from becoming live if something is broken. However, we can see that in this diagram the copper wire is coated in insulation and insulation again. Insulation is a material that does not conduct electricity. So if someone did touch the light, even if the copper wire was live, they would not get an electric shock because there's a lot of insulation. Or in other words, since the casing is not made of metal, there is little chance of an electric shock. So the casing not being made of metal or being an insulator is 1 mark, and the second mark is very little danger of electric shock. Write down the equation that links charge flow, current and time. The symbol for charge flow is Q, and the symbol for current is I, and the symbol for time is T. An equation that you should remember is QUIT, or Q equals IT. So the equation that links charge flow, current and time is charge flow, or Q is current times time. There is a current of 2.95 amps in one of the copper wires for 60 seconds. Calculate the charge flow through the wire. Use your equation from the last question. In the last question we found the equation charge flow is current times time. We want to find charge flow or Q, and we're given current and time in the question. So we can just substitute in our values. The current from the question is 2.95 amps and the time is 60 seconds. So we can just plug in these values to get our answer. But first we need to check the units. Amps is the standard unit for current and seconds is the standard unit for time. So we just plug these in to get an answer of 177. The standard unit for charge flow is coulombs, so coulombs is the correct unit. We get 1 mark for this calculation and 1 mark for the final answer. Figure 7 shows a current potential difference graph of a piece of copper wire. We can see the graph shows the relationship between current and potential difference. Draw another line on figure 7 for a wire with a different resistance. Okay, so we want to know what this graph would look like if we were using a different wire with a different resistance. We can start off by trying to find out what figure 7 tells us about the resistance of the piece of copper wire. We can try and do this by using the relationship potential difference is current times resistance. If we divide both sides of the equation by I, we get V divided by I is resistance. Gradient is difference in y divided by difference in x. That means in this case the gradient is current divided by potential difference. We can see from this rearranged equation here that the gradient is the inverse of the resistance, so the gradient is 1 over r. This tells us that if we change the gradient of this graph, we're changing the resistance. So another y with a different resistance would be the same but just with a different gradient. The line that we've just drawn has a lower gradient, which means that the resistance is going to be higher because the gradient is 1 over the resistance. To get both marks, we need to draw a straight line through the origin with a different positive gradient. The gradient has to be positive because resistance is always positive. Some fuses have a thin piece of copper that melts if the current is too large. Draw the circuit symbol for a fuse. We just need to remember this symbol and it looks like this. That's our answer. The circuit symbol shows that a fuse is made up of a component with a thin wire going through it that melts if the current is too large. So this is a helpful way to remember the circuit symbol. Describe how the movement of the copper particles in a wire changes when copper melts. This question is just like any other question which asks us to describe the movement of particles in a substance when the substance melts or changes from a solid to a liquid. So in a solid, the particles look like this. The particles vibrate around fixed positions in regular arrangement. However, in a liquid, the particles look more like this. In a liquid, particles are no longer in a regular fixed pattern and they have a bit more energy so they can move about each other a bit more. So when a substance melts, the particles change to being free to move around. Old copper wires are melted when they are recycled. Calculate the energy needed to melt 500 kilograms of copper at its melting point. Specific latent heat of fusion of copper is 200 kilojoules per kilogram. Use the physics equation sheet. We want to find the energy needed and we're given the mass and the specific latent heat of fusion of copper. We need to look at the physics equation sheet to find an equation which involves these values. And we can find the equation E equals ml, or thermal energy for change of state is mass times specific latent heat. So what we need to find in the question, or the energy needed to melt 500 kilograms of copper at its melting point, is also known as the thermal energy for the change of state. And for this we need to know the mass, which is 500 kilograms, and the specific latent heat of fusion for our material, which is 200 kilojoules per kilogram. Kilogram is the standard unit for mass. However, kilojoules per kilogram is not the standard unit for specific latent heat. The standard unit is joules per kilogram. So we need to convert this, and to go from kilojoules to joules, we times by 1,000. So we get 200,000 joules per kilogram. So now we can substitute in our values to the equation. And we get a value of 100 million joules. We get 1 mark for the conversion, 1 mark for the calculation, and 1 mark for the final answer. Radioactive nuclei can emit alpha, beta, or gamma radiation. Which type of radiation is the most penetrating? So what is alpha, beta and gamma radiation? Alpha radiation is made up of 2 protons and 2 neutrons. It is also a helium nucleus. Beta radiation is made up of high-speed electron, and gamma radiation is a type of electromagnetic radiation. What does penetrating mean? Penetrating is how easily something can pass through a material. And we compare how penetrating each type of radiation is by comparing what it takes to stop that radiation. So alpha radiation is big and bulky and can be stopped by just a single piece of paper. Beta radiation can pass through paper, but it is stopped by a few millimeters of aluminium. Whereas gamma radiation can pass through both paper and a few millimeters of aluminium. It takes several centimeters of lead to stop it. We can see that gamma radiation can pass through the most materials, so that is the most penetrating, and alpha radiation is the least penetrating. Which type of radiation is the most ionizing? Well, what is ionizing? Well, when atoms and radiation collide, the radiation can sometimes cause atoms to lose electrons, and this means that they form ions, because ions are atoms with an imbalance of charge. Radiation that's the most ionizing is radiation that causes atoms to lose the most electrons. Alpha radiation is big and heavy. It is bigger and heavier than beta and gamma radiation. This means it causes the most atoms to lose electrons, so it's the most strongly ionizing. Beta is less big and heavy than alpha radiation, so it's less ionizing than alpha. Whereas gamma has no mass at all, so it is only very weakly ionizing. Which type of radiation has the longest range in air? So alpha, again, is the biggest and heaviest type of radiation. This means alpha particles collide a lot with particles in the air, so it can only travel a small distance before being stopped. Beta radiation is smaller than alpha radiation, so it collides less with air particles. However, gamma radiation is a type of electromagnetic wave, so it can travel much further than alpha or beta radiation before being stopped, so it has the longest range in air. When radioactive isotopes in the Earth's crust decay, they release energy. The decay causes the heating of rocks in the crust. Figure 8 shows the decay of uranium-238 into thorium-234. Complete Table 2 to show the number of neutrons and protons in the nuclei. So from figure 8 we're given uranium as this. When we're given an element like this, the top and bigger number is the mass number, and the bottom number is the atomic number or the proton number. The mass number is the number of protons and neutrons, and the atomic or proton number is the number of protons. The atomic number is 92, so that means there are 92 protons in uranium-238. We can do the same thing for thorium. We know that 234 is the number of protons and neutrons. We also know that 90 is the number of protons. So that means the number of neutrons, which is what we're trying to find, is 234 minus 90. And that gives 144. So there are 144 neutrons in thorium-234. Geothermal power stations pump water through heated rocks. The temperature of the water increases from 20 degrees C to its boiling point of 100 degrees C. Calculate the change in thermal energy when the mass of water heated is 150 kilograms. Specific heat capacity of 4,200 joules per kilogram degree C. Use the physics equation sheet. From the information in the question, we're given a temperature change of 100 minus 20 degrees C, which is 80 degrees C. We're given a mass of 150 kilograms and a specific heat capacity of 4,200 joules per kilogram degrees C. We need to look at the physics equation sheet and find an equation which involves the change in thermal energy and these three pieces of information. And if we look, we get the equation E equals mc delta theta, or mass times specific heat capacity times change in temperature is energy. If we use these values, we would be calculating the change in thermal energy when 150 kilograms of water changes temperature by 80 degrees C. And this is what the question is asking us to find, so that is the right calculation. But before we type that into our calculator, we need to check the units. Kilogram is the standard unit for mass, joules per kilogram degree C is the standard unit for specific heat capacity, and degree C is the standard unit for temperature. So our units are correct. If we type that into our calculator, we get an answer of 50,400,000. Joules is the standard unit for energy, so that is correct. This question is 3 marks. We get 1 mark for working out the change in temperature, 1 mark for this calculation, and 1 mark for the final answer. Figure 9 shows 2 models of the atom. And we can see there's the plum pudding model and the nuclear model. Write the labels on figure 9 using the answers from the box. So if we look at the labels on the plum pudding model, so the plum pudding model is an outdated model of an atom, and it stated that an atom was made up of a ball of positive charge with negative charges spread throughout it. A negative charge is called an electron, so that is here. The second arrow on the plum pudding model is pointing to the whole diagram, and that is an atom. The first label on the nuclear model diagram is pointing to the center of the atom. The center of an atom is where the mass is concentrated, and we call that the nucleus. The second label on the nuclear model is pointing to the path of an electron around the nucleus, and we call that an orbit. We've correctly matched the terms from the box to the labels to get 4 marks. Explain why the total positive charge in every atom of an element is always the same. To answer this, we can think about how we categorize elements. If we have a bunch of atoms, how do we decide which ones are hydrogen or magnesium or any other element? Well, we do this by saying all atoms of the same element have the same proton or atomic number. And the proton or atomic number is the number of protons in the nucleus. This means that the total positive charge in all atoms of an element is always the same because all elements have the same proton number, and the number of protons is what determines the total positive charge. This is because all protons have the same charge. So we get 1 mark for saying all elements have the same proton number, and a second mark for saying the proton number is what determines the total positive charge. The results from the alpha particle scattering experiment led to the nuclear model. Alpha particles were fired at a thin film of gold at a speed of 7% of the speed of light. Determine the speed of the alpha particles. The speed of light is 300 million. So the speed of the alpha particles is 7% of the speed of light. If we want to find a percentage of a value, we times the value, or in this case 300 million meters per second, by the percentage as a decimal. So 7% as a decimal is 7 divided by 100. You can also write this as 0.07. To convert from percentage to decimal, you always divide by 100. If we type that into our calculator, we get an answer of 21 million. The units stay the same because we're timesing by a ratio which doesn't have units. So our final answer is 21 million. We get 1 mark for this calculation and 1 mark for the final answer. Figure 10 shows 2 atoms represented as solid spheres. A hydrogen atom has a radius of 2.5 times 10 to the minus 11 meters. Determine the radius of a magnesium atom. Use measurements from figure 10. So one way we could answer this is by measuring the radius of the hydrogen atom, and then measuring the radius of the magnesium atom, and dividing the radius of the magnesium atom by the hydrogen atom to find how many times bigger the magnesium atom radius is than the hydrogen. So if you do this, you should get an answer of 6. So that means the magnesium radius is 6 times the hydrogen radius. So that means if you times the hydrogen radius by 6, you get the magnesium radius, which is what we want to find. So the hydrogen radius is 2.5 times 10 to the minus 11 meters times 6. It gives us an answer of 1.5 times 10 to the minus 10 meters. So that is our answer. We get 1 mark for this calculation, timesing it by 6, and a second mark for the final answer. A student wanted to determine the density of the irregular shaped object shown in figure 11. We can see there's what looks like a little chess piece. Plan an experiment that would allow the student to determine the density of the object. Okay, we want to find the density of this object, but we don't have, in a normal science lab, an instrument that will just measure density of objects for us. But we do know that density is equal to mass divided by volume. So if we find the mass and the volume, then we can work out the density. We know how to measure mass. First, measure mass using scales. But how do we measure volume? We know with some shapes, for example a cube, you can just measure the height, the width, and the depth, and times them together and you'll get the volume of the cube. And you have similar equations for different types of regular shapes like a sphere. But this object is irregular. If you wanted to measure the volume of the objects in figure 11 like that, you'd have to take lots and lots of measurements and do lots of really complicated math. It would be nearly impossible. So you can't do that. So we have to find a different way to measure volume. Instead, we use the fact that when you submerge something in water, it displaces its own volume. For example, if you put water in a measuring cylinder, if you put in a cube with a volume of 3 centimeters cubed into this measuring cylinder, the measurement of the water will increase by 3 centimeters cubed. So if you put an object in water, the change in the measurement of the water volume is going to be the volume of the object. So you should part fill a measuring cylinder with water, measure the initial volume, then place the object into the water and measure the final volume. The final volume minus the initial volume is going to be the volume of the object. Alternatively, there's a slightly different method you can use. It uses the same principle of putting an object in water and then seeing how much water the object displaces. Instead, for this method, you use a displacement can, which is a beaker with a spout in it. You fill the water level to just below the spout, and this means that if you put an object in it, any displaced water will flow through the spout and can be collected, and then this volume could be measured. The measured volume of water will be the same as the volume of the object. Carrying on with the first method, so we've now found the mass and we've found the volume. For the last part, we need to state that to find the density, we divide the mass by the volume to get our answer. To get 6 marks, we need the method to lead to a valid outcome. We need all steps to be identified, and it needs to be logically sequenced. We also need as many indicative points as we can. We get a first indicative point for saying we'd measure the mass, and another one for saying using scales, and a third for saying we'd part fill a measuring cylinder with water. Then we get more for saying measuring the initial volume, placing the object in water, and measuring the final volume. Another one for stating that we find the volume of the object by subtracting the initial volume from the final. And a last one for stating this equation. This answer is enough to get 6 marks, but if you use the other method, you get indicative points for saying fill a displacement can with water, water line with the spout, place an object in water, collect the displaced water, and measure the displaced water. Another student did a similar experiment. He determined the density of 5 common plastic materials. Table 3 shows the results. The table shows 5 plastic materials: acrylic, nylon, polyester, polystyrene and PVC, and their densities. Figure 12 shows the results plotted in a bar chart. We've also written down the information for the table so it's easier to read. To complete figure 12, you should write the correct scale on the y-axis and draw the bars for polyester, polystyrene and PVC. First we need to put the scale on the y-axis. One way to do this is we know that nylon has a density of 1,000 kilograms per meters cubed. So this point on the scale must be 1,000 kilograms per meters cubed. We don't need to write the units here because the units are already written on the label. We can use this to work out the value of one little square. We can see that there are 5, 10, 15, 20 little squares up to this point. So that means 1,000 divided by 20 is going to be the value of one little square, and that is 50 kilograms per meters cubed. There are 5 little squares in a big square, so that means we can find out the value of one big square by doing 50, the value of one little square, times 5 is 250. We can use this to fill up the axis. So 250, one little square, two little square is 500, 750. Add 250 to 1,000 and we get 1,250. Add 250 again to get 1,500, and again to get 1,750. Next we need to add in the bars. Polyester has a density of 1,380 kilograms per meters cubed. So where does that go? 1,380 is closest to 1,250. And if we do 1,380 minus 1,250, we get 130. So the polyester line is this height here plus 130. Each little square is 50, so adding 2 squares gets us up to 100, but then we need 30 more. So our line is 3/5 of one little square above that point there. So that's the height. The width of the other bars are 4 squares, so the width of our bars should be 4 squares. Polystyrene density is 1040. 1000 is here, and then plus 40, so plus 4 over 5 of a little square. So that's here. And PVC density is 1100. Again, 1000 is here, and then plus 100, which is 2 little squares. We get 2 marks for at least 3 correct y values, and then another 2 marks for all the bars drawn to the correct height. And this has to be within half a square. A student is given a piece of plastic material. The student determined the density of the material 3 times. Table 4 shows the results. Determine the uncertainty in the student's results. So uncertainty is the range divided by 2, or the maximum value minus the minimum value, all divided by 2. So in this case the uncertainty is 1120 minus 960 divided by 2, and it has the same units as the measurement. So it is 80 kilograms per meters cubed. We get 1 mark for this calculation and 1 mark for the final answer.